Hello students, let us start our session of chapter number 5, Laws of Motion. Here, while we want to move a body from the rest condition, or if body is in uniform motion and if we want to make it stop, always external unbalanced force is required. These external forces can be a contact force or non-contact force. Non-contact forces are gravitational force, electrical force and magnetic forces. And contact forces, which is known as a pulling force, pushing force, string tension force, like frictional force, likewise. So here, to make a change in the state of the object, some external force is required. Now, here, let us understand the fallacy given by the Aristotle. Aristotle viewed that a body is in a moving continuously. So, to keep that body in moving, some external force is required. So, here, this external force which keeps the body in motion. If we want to make it stop, then that external force is going to be removed. If this external force is removed while that object is in moving, then this object covers certain distance and eventually it will stop to move further. So due to which condition this object will stop to move further? That is due to a frictional force. So here this frictional force is present between surface of the object and a ground. This frictional force which provides the external opposite force while that object is in a motion, and due to this friction object covers certain distance and then it will move to stop further. So this is the opposing force that will be present between any two objects which is in a contact. These two objects can be different types. One object can be solid and another one can be a fluid. For example, if any solid object we are dropping in the water filled bucket, so that object will feel a buoyancy based on the friction force. So these forces are external forces. Now, if we want to change the condition of that object, for example, if object initially in a rest condition, if we want to make it motion, if we want to move that particular object, then how much minimum force is required? As frictional force is present, so that external required force, at least minimum value of the frictional force and in the opposite direction. So, external required force must be equivalent to the value of frictional force in the opposite direction, then only objects start to move in a particular direction of the given force. But here, Aristotle give you the wrong understanding. He coded this practical experiment in the basic of argument. But if we want to get a particular conclusion, so with the law of nature for forces and motion, he has to imagine a world in which uniform motion is possible with no frictional forces, and that is understood by the Galileo further. Now, conservation of momentum. Basically, momentum is the mass of the object and velocity of that particular object. Here, if external force is not present, then between two objects, mutual forces of the pair is available. These mutual forces are equal and in opposite direction, and their total equivalent momentum will cancel out to each other. So here this total momentum is conserved by interacting with the particle. Let us consider two objects A and B. Object A having the initial momentum PA and object B having initial momentum PB. Let us assume that both objects are moving in a same direction and object A having higher velocity than object B. So, after covering certain distance, object A will collide with object B at a particular point. After this collision, their individual momentum will change and it will be considered as denoted as P dash A and P dash B respectively. So here, this change in the momentum of a particular object will define the force. That from object A to object B, how much force is applied, that is FAB in a particular time, that is FAB into delta T equal to P dash A minus PA. And same, object B will provide force onto the object A, which is known as a reaction. So this FBA into delta T equal to P dash B minus PB. So from object A to B, let us consider as an action, and from object B to A, whatever the force is defined, let us consider as a reaction. As per the Newton's third law, action and a reaction are equal and in opposite. Based on that, we can say that FAB equal to minus FBA. Let us substitute the value of forces from the above equation, and resultant equation we will get P dash A plus P dash B equal to PA plus PB, which defines that total final momentum of objects equal to total initial momentum of that particular object. This conservation of momentum is applicable for collision in elastic or inelastic. For the elastic collision, kinetic energy also remains same before collision and after collision. Now let us understand another topic, equilibrium of a particle. Equilibrium, it means the net total external force experienced onto the particle, it should be zero. For that, whatever the number of forces are applied onto that particle, but their resultant effect of all these forces should be zero. So here, let us consider two forces, as you can see in the diagram, F1 and F2. These both forces are having the same magnitude, but both applied in the reverse direction, in opposite direction. And that's why at a particular point, their net effect is zero. Likewise, as you can see in the diagram, if three forces are there, F1, F2 and F3, then also their net effect at the particular point would be zero, which this condition is known as equilibrium condition. Here, all these three forces, F1 and F2 and F3, are in a vector condition. So to get its resultant value, we can use parallelogram method or triangle method. For the parallelogram method, let us obtain the resultant value of F1 and F2, and that result will be analyzed with the third force F3. So here, by using this method, we can get a resultant value and it should be zero. These forces are in terms of vectors, so their resultant sum in each direction of axis would be zero. That, for example, let us take x direction. So F1x plus F2x plus F3x would be 0. Likewise, F1y plus F2y plus F3y equal to 0. And accordingly, with the same manner, F1z plus F2z plus F3z equal to 0. So, the resultant effect in each direction again will give you the equilibrium resultant effect. Let us go through the example for the same. A mass of 6 kg is suspended by a rope of length 2 meter from the ceiling. A force of 50 Newton in the horizontal direction is applied at the midpoint P of the rope as shown in figure. What is the angle the rope makes with the vertical in equilibrium? Neglect the mass of the rope. So here let us define first a force is defined at the particular point. As you can see in the diagram B, we are taking a reference point W, and onto that W let us draw free body diagram. Free body diagram, it means on that point how much forces are applied that we are going to consider. So on that W, that is the mass of the object on which two forces are applicable. At the downward side, the force is mg, and let us consider at upward side the normal force is there denoted as a T2. So mg, that is m, mass of the object, that is given of 6 kilogram, and g, that is already given, that we are supposed to take 10 meter per second square. So mg force applicable onto the object on W point, which is a 60 Newton, defined at a downward side. And normal component of force onto the mass of the object onto the point W, which is upward side, which is denoted as a T2. And as we know, these two forces are in opposite direction. For the equilibrium condition, both values supposed to be same, as object is not moving. So object is stationary, means both the forces are having a same magnitude and opposite direction. From that condition we can say that T2 also having 16 Newton. Now let us draw free body diagram at point P, at the center point of the rope. At that point, three forces are applicable. One is T2 force, which is a downward side, that is towards the object W. As in the example it is given, at point P, horizontal force is applied, that is a 15 Newton in the horizontal direction, and from the ceiling that force is available, that is a T1. So here three forces are there, T1, T2 and horizontal force 15 Newton. So horizontal and vertical components of these forces, let us denote it as T1 cos theta, that is equal to T2, and that is T1 is 60 Newton into T1 sin theta, that is equal to 15 Newton. So from that, let us equate both the equation, and we are having tan theta equal to 50 Newton divided by 60 Newton, that is equal to 5 by 6. So theta equal to tan inverse 5 by 6 equal to 40 degree. So here this answer does not depend on the length of the rope nor at the point at which horizontal force is applied. Now let us go through the another topic, common forces in mechanism. In mechanics, every object onto the earth basically experiences a force of gravity. This gravitational force is available due to the earth. This gravity force is available onto each object by the same value that can be act at a distance, that is a non-contact force. Other forces in that mechanics are the contact forces that can be applied on solid or fluid. When two bodies are in contact, their mutual contact forces satisfied the condition of Newton's third law. Based on action, any reaction forces are present, equal and opposite. The component of this contact force normal to the surface of the contact, which is known as a normal reaction. The component of the force which is parallel to the surface in contact, which is known as friction force. These contact forces are also present between solid and fluids. Let us go through some of the examples regarding this contact force. As in first example, it is defined that by the rope that object is tied and these two forces are applicable, mg and normal force T. In second example, that spring is available. Onto this spring, one object is tied and both are experience the forces. In third example, the contact force is defined between solid and fluid. So likewise, contact forces are applicable between any two objects. They can be a same type or different type. So here, this other common forces are the tension force in a spring and force due to spring. When spring is compressed or extended by an external force, and it will restoring the force will be generated that is proportion to the compression or elongation. So spring force can be defined as F equal to minus Kx, where x is the displacement and k is the constant value. Negative sign defines the force in opposite direction to the displacement. Here, the force present in extensible spring, in extensible string, that is very much high, and a restoring force in a string that is known as tension force. So here it is customary to use a constant tension force throughout the spring. That is just the assumption, that is just an assumption for negligible mass. Gravitational force and electrical forces are relevant with the mechanics. These different contact forces of mechanics mentioned arises from the electrical forces. As we are talking about uncharged and non-magnetic bodies in mechanics. If we are taking a microscopic level of forces, so in that case, all bodies or charges are having a very small size, that is a nuclei or electrons, and various contact forces are available due to elasticity of objects, molecular collision, impact, likewise. And this can be traced to electrical forces between two charged different bodies. This microscopic origin of the force is complex and not useful at mechanics level. So here we are avoiding to go through that microscopic scale level forces. Okay, so here we are going to end this session. Hope you understood. Thank you.